We have one last slide to cover on the amines, and then we'll get into the new chapter material. So, amines can actually be made by the reduction of the nitro group, NO2. So if you think about, let's use a real example. Let's take like nitromethane. Okay. Anybody know what nitromethane is used for? Anybody heard of that before? Has anybody ever heard of top fuel racing? Fun cars, that kind of stuff? Nitromethane is used as a mixture of that and methanol. It's the fuel for those types of vehicles. Okay, so nitromethane is readily available, pretty inexpensive. But what you can notice here is that we already have the carbon-nitrogen bond, right, that would be required in an amine. And I can draw that a little differently to where you can see everything written out. That's what the nitro group looks like. Nitro has a positive charge. One of the oxygens is negatively charged, the other one is neutral. But what you can see here is that we have the carbon-nitrogen bond of an amine. So if I'm trying to compare that to an amine, right, that's the amine. You can see the carbon-nitrogen bond there, right? What kind of amine is this? Methylamine, but what kind of amine is it? Primary amine, right? Yeah, so it's a primary amine. What would I need to do to convert this into this? Okay, you're talking about the reagents, and that's fine, but I'm talking just fundamentally what do I need to do without worrying about the reagents.
Reduce it.
Okay, so what do I need to do?
Remove the oxygen and add hydrogen.
Right, I'm going to need to remove the oxygens. What you notice is that the nitrogen here, right, it has no lone pair. An amine has a lone pair, right? So somehow we've got to give it electrons, and that's what Selena was getting at. We're going to have to use some kind of thing that can donate some electrons. Okay, we'll get to that in just a moment. And as Jason mentioned, we're going to have to replace the oxygens with hydrogens. So that suggests we're going to need some kind of hydrogen source, right? And up to this point, right, you've learned about doing reductions, right? We can take alkanes and alkynes and we can reduce them to alkanes with hydrogen gas and palladium metal. That will work here. That'll work just fine. You can take hydrogen and you can take palladium and you can do this reaction without any problem. But there is an issue with this. Can anybody tell me what it is? Money. Right? Palladium is a very expensive metal. It's more expensive than gold. Okay? Gold is cheap to a chemist. Okay? Silver is dirt cheap. Palladium, iridium, platinum, those things are starting to get into some really pricey metals. Okay? And palladium is one of those expensive metals. So I'm taking nitromethane, which is cheap, and I'm going to make methylamine, which is cheap, and I'm going to use something really expensive to make it. That's not going to get you to keep your job, right? But there's another way, fortunately, that we can reduce nitro compounds to amines. We can use iron and hydrochloric acid, both cheap. Where can we get iron from? You can go to Lowe's right now or Home Depot and you can buy a bag of nails that are just pure iron. Cheap, right? You can go to Home Depot or Lowe's and you can buy hydrochloric acid. It's what they used to wash bricks with. Again, cheap, right? So I can take nitromethane, I can react it with iron and HCl, and I can ultimately get the amine. But will I actually get this product to start with? The answer is correct, no. But what will I get?
feel like the CO would attach somewhere and then have to leave.
Okay, not too far off. What do we know about amines? Are they acids or bases?
Bases,
They're bases, right? They got a lone pair of electrons, and they like to react with.
acid.
So the real product that we get at the start is the hydrochloride salt of the amine, the ammonium salt. So how would I get the amine then? What would I do after this reaction's over, Selena?
After this one's over.
Yep. So I just threw in the iron and the HCl, I reduced it to this, I get this, now how do I get the amine that I want?
Remove so the chlorine attacks the hydrogen.
Okay, but that would still give me HCl. So that really won't, this is perfectly stable. I know what you're trying to say, but I can't use the chlorine because that gives me a strong acid that'll just react again.
The iron.
Well, we've removed the iron already. All I gotta do is treat that with sodium hydroxide, right?
Oh,
And I generate the free amine. I just gotta neutralize the acid, so to speak. Plus you get water, plus sodium chloride. Okay. That's the reaction. Now, you can use iron and HCl, you can also use tin and HCl. Both of these will work just fine for this type of chemistry. Okay? And again, you can literally go to Lowe's, you can buy some nails, you can throw the nails in there with the reaction, throw some what they call muriatic acid, which is just dilute hydrochloric acid, stir it around, you'll make the ammonium salt, then you treat it with sodium hydroxide, which again you can buy from Lowe's. It's called Drano. That's what Drano is. It's a concentrated sodium hydroxide solution, and you can get the primary amine. All of the things that we're using here, even though there's a few more steps, are a lot cheaper than palladium. That's the take-home message. Okay? You can take iron and HCl or tin and HCl, and you can put it in the presence of a double bond. It will not reduce the carbon-carbon double bond. Okay? It's not a good enough reducing agent for that. But it's pretty good here. Okay? What's the oxidation state of the nitrogen in the nitro group? How many valence electrons does nitrogen come in with?
5.
5.
plus 1. Minus 4 for the bond.
Does it get any of these?
No.
Does it get any of those?
No.
Does it get any of those?
Yeah.
Does it? What's more electronegative, nitrogen or carbon?
Nitrogen.
Nitrogen, so how many does it get?
2.
Gets 2. It's in the +3 oxidation state. Yeah.
Oh, I was thinking formal charge.
Well, formal charge is positive for the nitrogen of the nitro group. That's right. As we have it drawn, but that's not how we calculate the oxidation state. Okay. So I want you all to figure something out real quick. Tell me how you would make aniline from benzene. You have to start with benzene, but you can do anything else that you want.
Make the nitrobenzene first.
Okay, write it down.
Oh, okay.
You all right there?
What are we doing again?
You're doing that reaction. How do you do that? When I look at these types of problems, I start to ask myself, how do I get to here from that, right? So I've got to kind of work backwards. I don't think backwards. I don't do backwards thinking, but I think backwards in terms of, I know where I want to go, and I know that I've got to get to where I can start from, right? All right, so what do I need? What is the difference between these two molecules? The difference is I've got a carbon-nitrogen bond. Do we know how to put an amino group directly on a carbon?
No.
No, I've not taught you any of that with this type of thing, right? We did learn that we can take alkyl halides and we can react them with ammonia and we can make that bond. That's not going to work here, okay? But we do know how to make a carbon-nitrogen bond through what reaction?
NO2.
Yep. And what did we call those reactions?
Nitron.
It's nitration. Okay, that's good. But in general, what's the type of reaction? 3 letters. EAS, electrophilic aromatic substitution, right? So I'm going to take, what am I going to use here? How am I going to get the NO2? Plus.
Nitric acid and sulfuric acid.
HNO3, sulfuric acid, do the reaction. I get the nitrobenzene, right? I've now made my carbon-nitrogen bond. Now all I've got to do is convert it to the amino group, and I can use nails and HCl. Right? Just iron and HCl, that's what I need to get there. Okay? So it's a step-by-step process. This ability to start with a product and work your way back is what we call retrosynthetic analysis. Okay? We're not going to talk a whole lot in this class about retrosynthetic analysis. Okay? But it's an important skill for a chemist to have. And this kind of thinking is very important for you all to have in your future careers. Some of you are in forensics, some of you are in nutrition, some of you are going to see patients or clients, right? But think about it, if you're in forensics, you walk into a crime scene, are you going to be thinking forward or backward? Backward. The crime has been committed, and you have to work your way backwards to what probably happened, right? This is important. You're seeing a client in your nutrition company or whatever you're doing, right? You see their current state. You got to give them advice on what they need to take to improve their health, right? You're going to be thinking backwards. You see the current state, you have to move back and to try to come up with a diagnosis. That's what doctors do every day, right? You come in, you've got certain symptoms, certain ailments, and they have to work backwards to what the likely cause is. Okay? So even though you all are not going to have a job in the future where you're making molecules from starting materials, the type of thinking that has to go on here is still very important to your overall career. So these are good exercises for you all to go through. It's like lifting weights, right, for a football player. I have never seen a football player on the field lifting weights, right? But they do it because they need to have that strength for game day, right? So that finishes up chapter 10 for us.
We do the chapter 9 towards the end.
We do. And so today we're going to start talking about, and I don't know why that says, yeah, I do know why. It's not chapter 2.
Chapter 11.
This is chapter 11, 11:1 to 11:4. Okay? Up to this point, you all have heard me say a time or two magic microscope. There is no such thing as a magic microscope. But we do have tools that allow us to determine things. And so far, you all have been very trusting of me of everything that I've told you. Right? But you shouldn't be trusting of me. We should always be skeptical. And your question should be, how in the world do I know we have what we have? How do I know that when I take benzene and I react it with nitric acid and sulfuric acid that I get nitrobenzene? How do I know that? right? If I did the reaction for you right here, you would see colorless benzene reacting with nitric acid and sulfuric acid, giving colorless nitrobenzene. You wouldn't be able to visibly look at that and say that anything has happened. And yet we know that things have happened. And we're going to talk about two forms of spectroscopy in this chapter. There are other types of spectroscopy, okay? But we're going to talk about infrared spectroscopy, and we're going to talk about nuclear magnetic resonance spectroscopy, okay? So we're going to go a little nuclear here, all right? And what do I mean by nuclear? I don't mean nuclear reactor, I mean the nucleus of an atom. Okay, that's what we're talking about, all right? So what you see right here is a rough diagram of one of our magic microscopes. It's a physics experiment, okay? It's a physics experiment. And it gives us a pattern, or what we call a spectrum, that tells us what's going on, okay? It allows us to interrogate the molecule in a way that we can determine what's happened. So, we need to start off by talking about the electromagnetic spectrum. Here's the electromagnetic spectrum, right? You all probably remember from your high school days that as we increase the frequency of energy, the energy goes up, right? So radio waves is actually fairly low energy. Cosmic and gamma rays, you probably learned, are high energy, right? You do not want to be exposed to cosmic and gamma rays. It will kill you, right? It's ionizing radiation. It will cut your bonds in half. It will kill you pretty quick. But y'all really don't fear radio waves, right? We're in the room right now. We're being bombarded by radio waves. Every one of your telephones that you have sitting on your desk are receiving radio waves right now, right? You're not fearful of those. Okay? So we know that energy is, as you increase the wavelength, the longer the wavelength, the lower the energy, the shorter the wavelength, the higher the energy. Okay? So we already know this, right? And if you look out here in the X-ray region, cosmic rays, gamma rays, high energy, right? About 10 to the 6, that's a million kilocalories per mole. That's a lot of energy. This will cause your molecules to ionize. This is what causes cancer. This kind of radiation causes cancer. You also know about visible light. We're looking at it right now. We know that the different colors have different energies, right? And we know that this is what is responsible for electronic excitation. Why are things colored?
Just it reflects that color.
It reflects that color, which means it has to be absorbing other colors, right? How is it absorbing those other colors? It's absorbing those other colors because electrons are being promoted from a lower energy level to a higher energy level. And that happens in the visible region of the spectrum. That's why we get colors. Out here in the infrared, where have you all heard the term infrared before?
CCTVs.
Pardon?
CCTVs.
CCTV, so closed caption, or not closed caption, closed circuit television, right? Outside your house, you put these up, they can see kind of in low light. They rely on infrared. What else?
Remote controls.
Remote controls use infrared. Okay, good. What else? Vision goggles, yeah, so night goggles are infrared goggles. They detect heat. Where else have you heard infrared? How about if you go to a fast food restaurant, or if you've ever worked at a fast food restaurant? Heat lamps are infrared, okay? So you're pretty familiar with infrared kind of stuff. And it turns out that infrared radiation causes molecules to vibrate and rotate. That's how it works as a heat lamp. That's why things get hot, because it's causing the molecules to vibrate and rotate. Okay? And when they do that, they rub up against each other, and that causes friction. And friction causes heat. Right? So that's why that all works the way that it is. Okay? So that's what we're going to be talking about today. On Monday, we'll be talking about radio frequency type energy when we talk about nuclear magnetic resonance. And you all know about nuclear magnetic resonance. You probably haven't heard it as a term. Many of you have probably had this done to you. It's called MRI. Magnetic resonance imaging is nothing more than nuclear magnetic resonance. Now, when chemists do NMR or nuclear magnetic resonance, you don't get a pretty picture of a tissue and all this kind of stuff. You get a spectrum that you have to interpret, but it's the same principle. So when they stick you in that MRI machine and you hear it doing its thing, we're doing a nuclear experiment on you, okay? And we'll talk more about that on Monday, okay? So, the way the infrared spectra are produced, we're going to take a sample of what we're interested in, and we're going to put a lot of infrared energy through it. And we're going to see what gets absorbed and what doesn't. And that's going to tell us something about the functional groups that we have in the molecule, okay? And so an infrared spectrum would look something like this. You've got on the y-axis what we call the percent transmittance. So if the energy is 100% transmitted, what does that mean? How much of it is absorbed? If it's being transmitted through?
Oh, then zero.
Zero, right? So 100% transmittance means that the molecule didn't absorb that energy at all, right? And so as we get lower in number, right? So if we had something that, let's say, absorbed had a percent transmittance of 25%, it would look like it would be a peak down here, okay? Now, we also have this thing on the x-axis called wave number. It's energy, okay? You all learned about frequency, you learned about wavelength, but for whatever reason back in the day, chemists decided to use this thing called wave number. Notice what the units are for wave number. It's reciprocal centimeters. So you take the wavelength, or you take 1 and you divide it by the wavelength, and that's the wave number. The nice thing about this is that it converts the wave number into energy units that are more easily understood. Because, right, if we have a long wavelength, the energy is low. But if I divide 1 by a big number, it's a small number, so it actually means a small energy. So it kind of makes things easier for us to interpret, okay? This is usually what you see. They've got some other things. You can also show it in absorbance, and you can convert other things, but just ignore these. Some spectra show that. And you'll get something that kind of looks like this. You get these little valleys. Okay, I call them peaks. They're just inverted, right? So what does this mean right here? Yeah, that's a really strong absorption. Whatever that wavelength is, right? So let's call it, that's 1,000, that's 2,000, let's call it 1,600, 1,700. This molecule, whatever it is, was absorbing that wavelength of light, or infrared energy, really strongly, okay?
So if it goes all the way down, did it absorb all of it?
It did. Yeah, it absorbed nearly all of it. Now, we're not quite to zero there, right? But it absorbed an awful lot of it, right? And you're going to be able to look at these different little dips, and you're going to be able to determine what kind of functional group your molecule has, okay? That's what infrared spectroscopy does for us. It allows us to determine what kinds of functional groups we have. Now, if you're real savvy with infrared, you can get more information than that, okay? But I don't know too many people that are that savvy with it, okay? But you can figure out what kind of functional groups you have, okay? And so these little peaks, as I like to call them, are typically called bands, but it shows you where energy is being absorbed, right? So right here, we've got some kind of absorption at about 3,500. We've got a little tiny absorption here, a little over 2,000, and you can start to use that information to interpret the spectrum and determine what you've got, okay? Now, you all have, or many of you have, a model kit. And let me build a model of a functional group. And I'm going to pick on the carbonyl, the C double bond O. And let me put another carbon on it just so we have something more. This model's a pretty good model. Right? I can see that things could rotate. I can see where things can't really rotate very well. Right? I can see that this is a carbon-oxygen double bond. I can see that that's a single bond. Right? That there's a hydrogen here, that there's 3 hydrogens there. This model works pretty good for most things, except one thing. This isn't how a molecule really looks. Okay? It tells me how things are connected, and it gives me an idea of the bonding. But molecules don't just sit there like that. They vibrate, they rotate, right? This molecule, I can't stretch it here, but in reality, this is really like an atom, a spring, and an atom. And in real life, these things vibrate, they rotate, they twist, they move, they dance in a lot of ways. And they will absorb energy and do that kind of thing. They will wiggle, they will waggle, they will weeble, they will wobble, they will fall down, kind of stuff. Okay? So this model really is a poor representation. But if you had high school physics, you probably learned about Hooke's law. Okay? And anytime you have two masses that are connected by a spring, right, those masses will stretch that spring a certain amount. Well, carbon has a different mass than oxygen, and bonds are kind of like springs. So we can use Hooke's law, okay? And so if you ever did the experiment where you took two masses and you stretch it and you let it go, you'll notice that it vibrates with a particular frequency. A heavier mass, if I lower it down and release it, it will bob up and down like this. If I take a lighter mass and I stretch it and I let it go, it will do this faster, okay? And so we can actually measure that through infrared spectroscopy, okay? You are not going to have to do this math, so don't panic on me. I'm not going to make you do the math. But this is Hooke's law. Hooke's law, okay, talks about the frequency of that vibration, and it's proportional, notice, to the mass of the atoms that are connected together, and this K, which is called a force constant. You probably learned about that in your physics class, the force constant of a spring, right? And it's easy to understand. You can go buy a cheap spring that you can easily stretch. Have you ever tried to stretch a spring that may be like on a pickup truck or on a garage door? You can't stretch them. They have different force constants, okay? And think about it. A single bond will have a different force constant than a double bond. Will have a different force constant than a triple bond, okay? And so we can use this information to determine what kind of functional groups we have, okay? So what do I want you to take away from this? I want you to take away from this that we're using classical mechanics, classical physics of masses and springs and applying it to atoms. And it works. It works really well for us, okay? It works really well for us. It's a great way to think about it. And that different bonds have different stiffness, okay? So they're like different stiffnesses of springs, okay? You need to know that that's all encompassed in Hooke's law, okay? I will not make you do the math, okay? So, let's move on. So here we've got a situation where we've got two atoms that are connected together. They're different. They're connected by a spring, okay? This is how it would be if you just set it on the table. But then I can put energy in it with my hands, right? And I can stretch that spring. And the amount of energy that I have to put in to get to that higher vibrational state, right, depends on the stiffness of that spring and the masses of the atoms. Okay, that's what this model tries to show us. And again, it comes down into Hooke's law, where we have the mass of atom A and the mass of atom B. Don't worry about why the math looks the way it does, but basically it's just dependent on the masses and the force constant. Okay? All right. So I'm going to jump ahead a little bit. And I'm going to give you the gist of it. This is roughly a IR spectrum. You'll see the wave numbers down at the bottom, and you'll see some functional groups that I've put in here for you. Okay? You're going to need to know this by memory. Now, don't panic about that, because it's real easy. All you have to do is reduce it to its fundamentals. All you have to do is reduce it to its fundamentals. Anytime I give you an IR spectrum, there's one place that you always start. This is worth writing down. You always start at 1500. When I give you an exam, it's on paper. Take your pen and find 1500 and draw a line. So draw a line at 1500. You'll notice I put a line in there already. Everything to the right of 1500, right? So all this area down here is what I call the fingerprint region. Fingerprint region is hard to interpret. Very hard to interpret for most people. Ignore it. Okay? We're not going to get to that level of expertise. But what you'll find is that this is really the SP3 region. Anything that's SP3 hybridized will vibrate and stretch in this region, in this fingerprint region. That's why it's like C single bond O. You'll see that kind of stretching. Okay? But think about C single bond O's. And then you think about C single bond C's, which will also be here. It all starts to overlap with a big molecule, and it's hard to interpret. So that's the fingerprint region. Just ignore it. Okay? And so you're going to start at 1500, and you're going to start moving to the left, which I call, in general, the functional group region. What are the steps that I need to take? So I start at 1500, and I'm going to move over how many wave numbers? What looks like the next line I've drawn in there for you? At about 2000. So I've got to move over 500 wave numbers. I'm going to draw another line. If you see some absorbances or some low percent transmittances between 1500 and 2000, you know that those frequencies belong to something that's sp2 hybridized. That's things like carbon-oxygen double bonds, carbon-carbon double bonds. So if you saw a peak here, you would know I've got to have something that's sp2 hybridized. Okay? I've got to have something that's sp2 hybridized. Now, between 2000, and again, I'm going to take another step of 500. So between 2000 and 2500, this is the sp region. This is where I'm going to find things that are sp hybridized. This is where I'm going to find things that are like carbon-carbon triple bonds, carbon-nitrogen triple bonds. You'll also find there, quite frequently, carbon dioxide. Now, why does carbon dioxide appear there when it has no triple bonds?
Because it has two double bonds.
It has two double bonds, so the carbon is what hybridization?
SP.
SP. Okay? And in fact, students will quite frequently be so close to the IR spectrometer when they're running their sample, their breath, you're exhaling carbon dioxide, you'll actually start to see the stretch of the carbon dioxide. Fortunately, it's pretty weak, so it doesn't really interfere too much, but you can see it. Okay? So, we've got the sp2 region, we've got the sp region. Now we have everything to the right of 2500. We call this the hydrogen region. This is where you're going to find the hydrogens of an organic molecule. You'll find things that are, CHs NHs, and OHs. You'll be able to see the hydrogens there. Okay? $1,500 to 2,000 is what region? SP2. 2,000 to 2,500? SP. 2,500 and on? Hydrogen region. 1,500 and below? Fingerprint. What are we going to ignore? Fingerprint. Okay? Why are we going to ignore it? Because it's just too complicated to interpret at this point. Right? All I'm going to hold you responsible for is functional groups. Okay? You need to have those regions committed. If you're going to depend on your nose to know where 3 lines are on a spectrum, you're going to be wasting a lot of time. So the first thing when I give you an IR spectrum, you're going to start where? 1,500, and you're going to draw some lines. Where are you going to draw those lines? 2,000 and 2,500. And I would go and label them. SP2, SP, right? If you see something in the SP3 region, or excuse me, the SP region, and I've got 3 molecules for you to choose from, and 2 of them don't have anything that's SP hybridized, they can't be the answer, right? So, process of elimination will be important in this as well, okay? This is like putting together puzzles. If you enjoyed putting together puzzles as a kid, or if you still like putting together puzzles, you're going to love spectroscopy. There are people that really love this. My graduate student loves spectroscopy. Okay? He loves to be able to look at a molecule and try to figure out what it is, or an unknown, and try to figure out what it is based on spectrum. Okay? It's how we know what we know, is by looking at how molecules interact with electromagnetic radiation. Okay? All right, so things can actually get a bit more detailed. Okay? You don't need to write down the 1,500, 2,000, and 2,500. But what you do need to know is that there's some subtleties within those regions that I just gave you. Okay? So for example, for the stretching of a carbon-hydrogen bond, it depends on whether we're talking about that hydrogen being attached to an alkane, an sp3 hybridized carbon, an alkene, an sp2 hybridized carbon, or an alkyne, an sp hybridized carbon. You'll see those hydrogens a little differently. Notice that an alkane, you'll see those hydrogens between 3,000 and 2,850. You'll see alkenes about 3,100 to 3,000, and you'll see alkynes at about 3,300. So it goes alkane, alkene, alkyne when we're looking in the hydrogen region. Okay? You'll see separate peaks for these types of hydrogens. And it has to do with the fact that, right, increasing force constant. An alkyne is a stronger spring than an alkene, is a stronger spring than an alkane. Okay, so it makes a difference. Okay? You'll see carbon-carbons in different regions, right? This is in the what region? That's in the fingerprint region. We're going to ignore that, right? But notice, I'll see carbon-carbon double bonds at around 1,600 to 1,680. And I'll see carbon-carbon triple bonds around 2,100 to 2,250. Okay? Again, increasing force constants. If I look at the carbon-nitrogen bond stretch, I'm not going to throw it up there yet. Tell me approximately where we'll see a C single bond end. In what region?
Fingerprint.
No, wait,
Fingerprint.
Pardon?
Fingerprint.
That'll be the fingerprint because it's single bonds, right? We'll most likely see that in the fingerprint region. What about a C double bond end? Where would that region be?
1,500 to 2,000.
1,500 to 2,000. That's P2 region. And C triple bond end?
2,000 to 2,500.
2,000 to 2,500. That's going to be in the SP region, right? Okay? And in fact, that's what we see. That's below 1,500. That's between the range that Jason just mentioned, and so is that. Okay? You're going to find these different things in these different areas. Okay? You need to know the rough ranges. It's just like PKAs. You kind of got to know the rough ranges. Okay? Don't rely on your notes for that. Commit this to memory. Okay. Your book has tables that look like this. They're called correlation tables. You can find an example. This isn't the one from your book, but you can find an example on page 346 where you can actually look up the specific frequency of a stretch or a vibration, and you can kind of correlate it to what the functional group has to be. You will not need to be this detailed for my exams for you. This would be what I would expect in 255 or 256 for organic chemistry. This is what I would expect of my graduate students. I need you to understand that there's rough ranges that are going to be there, right? But look at this. I mean, here's a bunch of things that are attached to hydrogens, right? You can start to see that they kind of break out into kind of unique areas. There is some overlap, of course, so you've got to know some other things. Looking at carbon-oxygen double bonds, well, if it's aldehydes, ketones, esters, carboxylic acids, or amides, they all kind of have some unique stretching regions. So you can determine an aldehyde kind of versus a ketone, but they overlap too, don't they? So you've got to look at some other things as well.
Can you give us an example of like the most detailed you'll get so we know
Yeah.
where to stop?
Yeah, we'll get to it. We'll get to it. Okay. So, in general, what would you expect this to look like? Where would you expect things to be?
Just to see carbon-carbon single bond will be in the fingerprint region.
Fingerprint region?
And then the carbon-hydrogen bond will be above 2500.
Be above 2,500, probably around 3,000-ish, right? And in fact, that's what we see. Right, so here's an exact one. So we would start at 1,500. Right, you're seeing all this stuff in the fingerprint region that you just mentioned. It's right over here below 1,500. But notice you see a lot of little bitty tiny things. Here's some CH bending. So a carbon-hydrogen bond, not only can it stretch, but it can bend. So you can see that. And then you can see the CH2 bending and stretching, right? There's nothing between 1,500 and 2,000, that's just flat. There's nothing between 2,000 and 25, where's 2,500? 2,500 right in there. It's flat. It's about 100% transmittance, right? But notice here we start to see something in this hydrogen region, right? And we're starting to see the different types of hydrogen. That's about what an alkane would look like. Okay? Whether it's octane, nonane, pentane, hexane, they all kind of look the same. Okay? Now, for hexene, what's going to start changing? Where am I going to start to see stuff?
The 22,000 to 25 to 2,500.
If it was a triple bond. This is a double bond.
So the 1,000 to 2,000.
Okay, so somewhere between 1,500 and 2,000, right? So this is what hexene looks like, one hexene, right? We can have other types of hexene. But what you can see, right, there is 1,500. There's all the fingerprint region. You'll notice that it looks different than octane, even though it still has some sp3 hybridized stuff, right? But it's different. It's hard to interpret. But notice when I look at between 1,500 and 2,000, I see this. That's a carbon-carbon double bond stretch. I can see it. Would you say that that's a real strong absorption or kind of a moderate one or weak one?
Moderate.
Moderate.
It's kind of moderate. And the reason that it doesn't go all the way to the bottom is because when I stretch the carbon-carbon double bond, I don't change the molecule's dipole very much. And infrared depends on changes in the dipole. Okay? But it does change it a little bit, and so we do see an absorption. Okay? If I go from 2,000 to 2,500, I don't really see anything. You know what that little peak right there is? It's carbon dioxide. Somebody was breathing when they took this around it, and so it picked it up. It's a real weak absorption, but that's it. But once you start to notice, right, when you look at the hydrogen region, this piece right here, just under 3,000, Kind of looks the same as this, doesn't it? But notice there's this extra one here. That's the hydrogen that's attached to, or the hydrogens that are attached to the carbon-carbon double bond. Remember, it goes alkane, alkene, alkyne, right? And so that actually is separated out. So I know by looking at this that it's pretty much still going to be a hydrocarbon of some sort, and I've got a carbon-carbon double bond, and I've got an alkene hydrogen. So I've got some type of molecule that contains a carbon-carbon double bond. What else can I do? I can look at one hexyne, something that has a carbon-carbon triple bond. Okay? And again, what you see is there's 1500, there's all my fingerprint region. Doesn't really look the same. It's kind of unique, it's kind of complicated. But when I go from 1500 to 2000, do I really see much? No, there's a little bit of a bump there, little noise, but it's very, very weak. It's not clear. But when I go from 2000 to 2500, do I see anything? Yeah, I see that carbon-carbon triple bond. And again, is that strong, medium, or weak?
It looks weaker than
It looks weak. And again, because it takes more energy to stretch, and there's really not a change in the dipole, okay? As much as there is.
Is it harder to stretch a triple bond than it is a double bond?
It is. It is. And that's why it appears in the region that it appears in. But look at the hydrogen region again. Again, this stuff right here below 3000 looks the same as the others, right? That's all the alkane pieces that are in the molecules that they all share. But notice this one. That's the CH stretch for the hydrogen that's attached to the carbon-carbon triple bond. Would you call that strong, weak, or medium?
Strong.
That's strong. Why is that one so strong? That one was moderate.
Yeah.
This is really strong. When I stretch that carbon-hydrogen bond, it really does change the dipole moment quite a bit. Remember, alkynes are more acidic. It's easier to remove that hydrogen. So when I stretch this, I get a change in dipole moment that's pretty strong, and so you will see that, okay? So, what might be an exam question? I might give you a spectrum that looks like this and these three choices, and you have to figure out which one it most likely is, right? If I gave you this, yes ma'am.
I'm confused on like how you're getting the answers based off like just the formula. Like, I don't understand.
Off the formula.
Like,
I don't know that this formula is actually correct for these spectra, other than the fact that we ran these spectra. I can't get that there's 8 carbons from this spectrum. What I can get is what kind of functional groups I have. This has to be an alkane. This has to be an alkene. This has to be an alkyne. That's what I can get. I can't get the actual formula from an infrared spectrum.
How do you know the range? Like for the other one, we said it was 1500 to 2000. How do you know like when to start and when to stop?
We know the ranges from Hooke's law, so you can actually go through and do the calculations and figure out where these things must be. But for you all, you need to memorize the ranges that I've given you. So it's going to be 1500 to 2000, 2000 to 2500. You draw those lines in, you have the ranges for the spectrum.
Okay, how do we know which peak specifically to look for? Like you said, you'd give us one of those, and then we know that if it peaks between 15 and 20, that it's the double bond, and if it's triple, then it's 20 to 25, and if it's 300, then it's the hydrogen. But how do we know which one to look at? There are a lot.
There are a lot of them, and you have to determine which ones best fit the molecules that you have. We'll work some examples. I think it'll be clear for you. Okay? So let's look at some other functional groups. Let's look at an alcohol. Okay, so we've got 2 alcohols. This is 2-butanol, or also known as second butanol. Okay? This is what the spectrum for that looks like. What can you tell me about the alcohols that are kind of unique?
The wide peak.
Yeah, you can get this broad peak that kind of looks like a parabola. This is telltale of one of two things. Either you have an alcohol or you have a solution that contains too much water. Because water also looks like this, okay? So this, anytime you see this at around 3,300-ish, your mind needs to think, I bet this is an alcohol. And what you can see is that they appear about the same place, regardless of whether it is a secondary alcohol or a primary alcohol. That's the nice thing about IR spectrum. The functional groups, regardless of what they're attached to, appear roughly in the same place. Okay? Now, I know that this spectrum has to belong to this molecule because it's got a benzene ring. Benzene rings have sp2 hybridized carbons. And I see carbon-carbon double bond stretching between 1,500 and 2,000. I know that this spectrum cannot belong to this molecule. Right? When I look from 1,500 to 2,000, there's nothing there for this molecule. Yeah.
When you give us one of those spectrums, you're not gonna have those little labels, right?
Nope. No, this is what I'm pointing out to you. But notice where that OH is. It's not overlapping with the CHs. You will see it distinctly like this. You'll see the CHs, and then you'll see the OH. Right? And that's what you're seeing here. You see the OH, and then you see the CHs. They are separated. Okay? Now, just a few things that you need to know about IR. We get IR spectra in what we call thin films, or we can do it in solution. We can make a solution of a molecule and go get an IR spectrum. We place it into what's called a cell, and the cell has to be invisible to IR, right? The IR energy has to be able to pass through the cell so that it'll interact with the molecule. And in the old days, we used things that were made out of sodium chloride, potassium chloride, or silver chloride. We made these plates. Okay, we would have two plates. It was a very expensive piece of salt. So they grow these big crystals of salt and they cut them. And you get it's maybe 1/4 of an inch thick and it's about the size of a quarter. And it's just salt. And you would polish it until it was transparent. You'd sit there and you would rub it on a cloth until it became transparent. You can actually see through salt if it's a single crystal. Huh? So it becomes a window. Well, when you're dealing with table salt, it looks white. But a single crystal of salt that's highly polished will be as transparent as glass. Okay? And it turns out these are ionic compounds, and ionic compounds don't really absorb IR radiation. So it makes nice. And so what I would do when I was a postdoc, I would take these salt plates and I would smear the molecule that I was interested in on, and I would take another plate and put on top of it. I would put it in the IR spectrometer and I would get my spectrum. The tough thing about this, right? Sodium and potassium chloride are soluble in water. So you can't go wash off your plates with water. You wash them off with, alcohol or benzene or something like that.
Wait, alcohol doesn't dissolve salt?
Alcohol doesn't dissolve salt very well. No. The water in the alcohol will help dissolve some of the salt. But I would use pure alcohol, rub off this stuff. So, a pair of, you guys go buy table salt for what, a couple bucks at thing at Walmart? A single sodium chloride plate back in the early 2000s was $100. And if you dropped it, it shattered and you had very expensive table salt that you couldn't do anything with. But today, have you all done anything IR in the lab? No? Maybe, hopefully you will. You actually don't use this kind of stuff anymore because students drop them all the time and we have these broken cells. So now we have a machine that actually has what's called an anvil on the top of it that's made out of IR optically transparent diamond. So it's a piece of diamond and you put your sample on it and then you
How is that less expensive than salt?
it's not less expensive than salt, but it doesn't break and it doesn't dissolve. So over time, it's cheaper than buying a bunch of salt. Right? So that piece of diamond, it's industrial diamond, is probably $500. right? But each salt plate is about $100. So it doesn't take too many students to break too many salt plates before it's cheaper to just go ahead and buy the bag, right, that you can't break or dissolve.
And you can use it over and over again?
Over and over again, you just wipe it clean and start over, yep, so it's reusable. So are the sodium chloride and potassium chloride cells, but when my wife was teaching organic and we used the older piece of equipment, she really freaked out one day when she saw a student over there at the sink trying to clean off. You know, you don't do that, okay? You can also run these spectra in solution. There are cells that are made where you can actually put liquids in. But again, the solvents for these things are typically organic molecules, which also absorb in the IR. So you have to be careful about that. And so we would use things like carbon tetrachloride or chloroform or carbon disulfide, which really don't give a whole lot of stuff except in the fingerprint region. Carbon disulfide would give something in the SP2 or in the SP region, excuse me. But it's a pretty weak absorbance. Carbon tetrachloride tends to cause liver cancer, so we don't really want you all working with that. And carbon disulfide catches on fire when you look at it wrong. So we usually don't want you all working with that either. So we kind of keep those things to ourselves these days. So let's work some problems. Let's work a few problems. This is kind of what you can expect to see on an exam. So you all get together, get in your groups, and try to solve this problem. I'm going to give you 3 minutes to solve this problem. You made it today? That's good.
Oh, yeah. Where do I start? You start at like
No, that's not a good question. Where do I start?
1500.
1500. What do I ignore?
Right.
Everything to the right. And where do I draw the next line?
2000.
2000. And where do I draw the next line? 2500. All right. So do I have anything between 1,500 and 2,000?
Yes.
Yeah, and it's pretty strong, isn't it? All right, so can I eliminate anything based on that single observation?
A.
I can eliminate A. And why can I eliminate A? Yeah, it's an alcohol, there's no carbon-carbon double bonds, there's no carbon-oxygen double bonds. I can eliminate that, and it can't be that. Plus, I also don't see a broad peak around here, do I? That look like an alcohol. Okay? So given that, can I eliminate something else as well?
D.
Yeah, D's got a carboxylic acid. The carboxylic acid has a C double bond O, but it's also got an OH. And that OH should also be appearing over here somewhere. I don't really see it.
OHs aren't at 3,000, they're 3,300, you said?
Yeah, they're a little further up, yeah.
So not here, okay.
Now, the carboxylic acid OH looks a little bit different, but I don't see anything other than typical CH. Okay? So, or at least right here, right? So now I've got choices of B and C. What do you think it is?
B.
B is the correct answer. Notice there's two hydrogens on this nitrogen. All I see are CHs. Okay? So if you looked at your correlation table in your book, you would have been able to note that those are CHs.
So is that just what a CH looks like? It's kind of.
It's got a bunch of stuff right there. Yeah. I mean, it will look a little different depending on the molecule, depending on how many CHs it has, but it's going to appear pretty much so right in that region. Oh.
Yeah.
What would, can you show what would, the end of two hydrogens look like, or the?
Yeah, somewhere right in here, you would have seen two peaks as well.
Does that just fall underneath the 3,100, 3,000?
Yeah, it's about that range.
So would you consider that an alkene?
No, it would be on the NH2. I mean, so it's a different chemical group. It does overlap a little bit, but not too bad.
Okay, and then what about the alcohol? What does it have to look like?
The alcohol has to be very similar to that.
So it has to be significantly wide then.
Oh, yeah. Yeah. It's,
Because we were discussing, I was like, we don't know how wide it has to be.
that's why.
So what, just somewhere between 3,500 and 33?
Yeah, somewhere in that ballpark. Yeah. Yeah. Try this one. Where do we start?
1,500.
And ignore
Right.
everything to the right. Where do we draw the next line?
2,000.
Do we have anything between 1,500 and 2,000?
Yes.
So we've got to have something that's sp2 hybridized, right? So can we eliminate anything based on that fact alone?
Yes.
What can we eliminate?
B.
We can eliminate B. We can also eliminate B because I also don't see an OH stretch, right?
Yes.
So we're gonna cross out B. 2,000 to 2,500 is the next region. Do I have anything there?
Yes.
Yes. Okay, what region is that?
That's B.
SP. Can I eliminate anything based on that?
Yes.
What can I eliminate?
D.
I can eliminate D. D doesn't have anything that's SP hybridized.
Yes.
So I just went from a 1 in 4 chance of getting the right answer to a 50-50. If I'm at the casino and I got 50-50 odds, I'm starting to place a lot of money on the table, right? 50-50 odds are great, right? So it can either be what?
A or C.
A or C. Which is the correct answer?
A.
Why is it not C?
Is it because of the hydrogen?
It is. If you notice, this has a terminal hydrogen on this alkyne, which should be somewhere over here, right? And it's not there.
After 2000, right? For the hydrogen?
Pardon? Yeah, it's about, here's the normal CHs, it's about right in this region. 33, 3,400, something like that. All right.
Wait. I wrote down the hydrogen is at 25 plus. The hydrogen region?
Yeah, it's at 2,500 and above, this is the hydrogen region, yeah. But remember, they can be broken down into smaller regions as well. So let's take a look at this one. Where do we start? 1,500. Do we draw the next line where? Do I see anything between 1,500 and 2,000?
No.
Okay. So that's the SP what region? And I don't see anything SP2 hybridized, so what can I eliminate?
All of them except C.
All but C. C is the right answer.
So if it falls right on the 1,500 line like that one does, you don't.
Nope, that's over here. 1,500 is the line. That's all in the fingerprint region. Okay. How about this one?
Guys, likely M minus size. No H. Sigma Y. That's drastic.
Where do we start?
2,000.
1,500. We draw another line at,
2,000.
is anything there?
Yes.
Can I eliminate anything based on that observation?
No.
No, I've got, every one of them has some kind of double bond, right? In this case, they're all C double bond O's. And so I can't eliminate anything based on that, can I? What do I do now?
Move on.
Move on. What do I do? Do you see anything in the SP region? Nothing significant. All right, like 2,000, 2,500, it's not really a whole lot there. But notice how this looks. It looks broad, right? But it's kind of jaggedy at the bottom, isn't it? Is that how an alcohol looks? No. So it probably doesn't have an alcohol. So what can I eliminate? Well, B's not an alcohol. It's a carboxylic acid.
D.
I can eliminate D.
Yes.
That's a real alcohol. Right? I got something broad that kind of looks like an alcohol, but it's really broad, and it's starting to overlap with all the CHs. That is characteristic of a carboxylic acid.
Wait, can you say that again? That last part you said.
The broad peak that you see here that overlaps with, and it's jagged at the bottom like this, right? It looks like a dirty alcohol, for lack of a better word, right? It's a carboxylic acid. Carboxylic acids stretch throughout the entire hydrogen spectrum. But because a carboxylic acid actually has the OH and the carbonyl, the C double bond O also has to be present. If you see something that looks like this and then this is not there, it can't be a carboxylic acid. Okay? All right. Quiz for chapter 9. Let's see what we got. Turn in 9.11, 9/11.
That's my birthday.
It's your birthday?
Yeah, very important.
It's my grandmother's birthday too.
I know so many people born on that day.
Were we supposed to draw